Hi. Okay, hold on. Just 1 second. Okay. All right. I was just trying to figure something out here. These proofs in this chapter are very wordy. Kind of gave you the outline already. Let's just I got rid of it. Just remember what I showed you in part A, having to do with that segment on ChatGPT that showed the different approaches to proofs. There's three different approaches um, to proofs regarding trees, and there's of course induction. There's the other two that I showed you as well, which has to do with building up, say starting from the trivial um, tree, which is just a node, okay, and building up by producing edges or producing vertices, and in both ways you're counting up the equal number of items, meaning that you've proved the theorem. Induction is usually the best way to do it, but what I'm trying to say is it's just there's just oh god, uh, it's just really worried. They're wordy. There's too many words. I'm not going to write it down. I'm just going to walk you through it. So, for example, here's a theorem: a graph G is a tree if and only if there is a unique, simple, and tidy. I'm not sure what tidy means here. Path between any two vertices of G. Tidy, and that's not a very mathematical term. Um, but simple is under to understand. Unique is simple to understand. So a unique, simple path between any two vertices. A graph G is a tree if and only if that's biconditional. That means it goes both ways. That means you have to prove it that a tree implies a unique, simple path between any two vertices, and that any two vertices of G that are a unique, simple path implies that it's a graph. The graph is a tree. So you have to prove it both ways, and that's what we do here. This is the proof sketch. So going this way to the right or going this way to the left, or you could just do logical equivalences and cut your time down in half, as we learned in the first chapter. So going this way, G if G is a tree, G is connected and has no cycles by definition. Multiple paths between vertices would form a cycle. That's a contradiction. So it's a unique, simple path. On the other hand, if there is a unique, simple path between every pair, G is connected. Paths exist. No cycles. Cycles imply multiple paths. That means G is a tree. Again, if there is a unique, simple path, obviously G is a tree. Conclusion: unique, simple path is biconditional with tree. So that's easy. So let's see how theorem 2 works. Every every tree with cardinality of where the vertex set is 2, greater or equal to 2, has at least two vertices that have degree 1. What does that mean now? They have two vertices that have degree 1, meaning there are leaves. Like you can't go anywhere else once you've hit that. So let's have a look and see what that means. Take any longest simple walk, x0 to xm, where there's m vertices in T. Both x0 and xm must have degree 1. Otherwise, there's a longer path in T. That is so simple. Okay? In simple terms, you're going from here to there, endpoints V1 and VK. Observation: if V1 had another neighbor outside this path, could extend the path, which is a contradiction. Every tree with vertex set V greater than or equal to 2 has at least two vertices that have degree 1. All right. Clearly, starting at the top, if you've got a rooted tree, well, that branches off into two, but every tree that has more than one vertex has at least two vertices that have degree 1. Again, it's this idea. These vertices here have degree 1. All right. Make sense? It just has to be the case. A pendant vertex, and I put this in here from, I don't know, some kind of wiki. Look, an end vertex or a leaf vertex is technically called a pendant vertex. So I just put that in here. So, it's in the context of trees, a pendant vertex is the terminal node or a leaf. Okay. So now you know this word. We can use it in this proof. Theorem 3, every tree with n vertices has exactly n minus 1 edges. This is kind of like the idea that you have, come on, it's so obvious. You've got a series of multiplications that are being added together, just like in matrix multiplication. So you got a times b plus a1 times b1 plus a2 times b2 plus dot 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 all the way to an times bn. Well, there are n multiplications and n minus 1 additions. So it's like partitioning that we did in repetition combinations with repetition. There was stars and bars, and n minus 1 definitely had to do with the count between stars and bars. There were n minus 1 bars partitioning the stars, the n stars. So a tree on one vertex has 0 edges, obviously. This is the base case. There are no loops. T, if T is a tree such that the number of vertices is greater than 1, it has a pendant vertex, I mean a leaf. Remove this vertex and its pendant edge to get a tree prime on n minus 1 vertices. By the induction hypothesis, T prime has n minus 2 edges, thus T has n minus 1 edges. Okay, so that is a very, very, very basic proof by induction. You start off with the base case, and then you make the assumption, and you go to that's the inductive hypothesis, and then you prove that you can get to the next leg in the ladder of the induction process. Okay, that's a very good example. Every tree on 2 or more vertices has at least one pendant vertex. It looks like I got this in the wrong place. This should have been before this, because there's always problems. Every tree on 2 or more vertices has at least one pendant. So again, all this is a proof by contrapositive. All this wordiness, there's just nothing really to write down. Like writing down formulas. I don't like writing down English. We just discuss it together. We walk through it together. So we use the contrapositive. You know what that means? Negate Q applies negate P. So every tree on 2 or more vertices has at least one pendant vertex. So you can see how that's A implies B. So suppose graph G has no pendant vertices. That's negate Q. All right. Starting at any vertex V, follow a sequence of distinct edges until a vertex repeats. This is possible because the degree of every vertex has at least 2. So upon arriving at a vertex for the first time, it is always possible to leave the vertex on another edge. Yes, when a vertex repeats for the first time, we have discovered a cycle. So that's not a tree if we discover a cycle. Therefore, proof by contrapositive. You see how that works? We're assuming that there are no pendant vertices, and then we argue it is not a tree. And that's what we get here because we have cycles. If you have a cycle, there's no tree. It's a nice picture. That's a really nice picture. I like the color contrast. I can't believe I took that picture. Again, Whistler. Paths, connectivity, and forests. Oh, God, we just keep repeating ourselves quite a bit here. Oh, by the way, I did clean this up. That's one of the reasons why I took a break, because I had to go through this again and try and make it cleaner. It's posted. The new trees PDF is posted on Canvas. So simple path, we know. Trees and paths. A tree has no circuits, cycles. Therefore, circles or cycles. Remember, these are two different things. Therefore, there is at most one path between any 2 vertices. 2 distinct paths between the same vertex would create a cycle, so we can't have that. Disconnected graphs. Well, that's for forests, right? A forest is a graph whose connected components are all whose Connected components are all trees is called a forest, and we already know that's just a bunch of trees that are um, uh, partitioned apart from each other. So here's an example. Consider the following disconnected graph. Okay, this is disconnected. We have a lone vertex, and then we have these two subgraphs. So this is a forest right here. So we defined on 9 vertices numbered 1 through 9 here. We can basically describe it this way. So this is one graph, this is another graph, and there's a final third graph that makes up our forest. So I could actually lay it out like this. For each edge in the original disconnected graph, we draw a corresponding edge between the same two vertices in the appropriate component. So note edges for 3, 7, 8, 9. There, these are just the partitioned subsets, subgraphs, subtrees, if you will, of that particular forest. Oops. So let's talk about rooted trees now. A rooted tree is when I decide maybe in this to take an arbitrary node and call it the root node I start from. So I go from here to here, I go from here down to there, and then this one branches into both 4 and 6. You see how that works. So we just choose one to be the root, and it's obvious in, say, a directory structure that you are a user, and you're the root of your subdirectory, but the entire directory structure has a root user, okay, the one who is at the top of the whole hierarchy. Of course, that's IT. If one vertex of a tree is singled out as a starting point and all branches fan out from that, we call that a rooted tree. So, of course, the terminology, come on, it's obvious. So, here, terminology. For each node V not equal to R, the parent is a unique vertex U such that the ordered pair UV is in the edge set. V is also called the child of U. It's too bad they don't have that, here. So see, you can say U goes to V. So V, the second one, is the child because U points to V. The edge goes from U to V. So V is the child of U. Two vertices of the same parent are called siblings. Come on, this stuff's all obvious. A leaf is at the end here. It's just a pendant vertex. The height of a rooted tree is the length of the longest directed path from the root to any leaf. So there it is. It's 2, length 2, height 2. The ancestors, descendants of a vertex V are all the vertices. Well, it just means everything that goes below there. So the ancestors of the root are all of these nodes. All right. What's that? The subtree, we know what a subtree is. Okay, we know what a subtree is. You could call this a subtree. This is a subtree. Okay. So going back to this, like I said, I'll just pick 2, from this example we gave before. I'll pick 2 as the root vertex, just the way I drew it out. The root's adjacent vertices are its children. The vertex with children is parent. Internal vertices, 5 is an internal vertex. Okay, that's the root. These are all leaves. There's one internal vertex. An emery root tree means it is at least having at most a branching factor of m. Okay, if no vertex has more than m children, then an emery rooted tree is what we have. If every internal vertex is exactly m children, it's a full. So, for example, let's look over here. So, this is a binary tree. That's a binary tree because it has a branching factor of 2, at most a branching factor of 2. But it might, all right, do something like this. But because of that, it is not a full binary tree. If it did this, then, okay, each node has a branching factor of 2, okay? Although this is really weird the way we've arranged it. This is it right here. You know what I'm doing. So this is a full binary tree. This is a full trinary tree. It gets messy after a while. You get the idea. Right. When m equals 2, it is a full binary rooted tree. Okay, so that's what we've just drawn over here. Examples. Look what we can do here. There, b's the root, and all of these are equivalent. Okay, this can be turned into this, which can be turned into that. This is the way we use it. We don't draw trees really like this, although it's valid, but a rooted tree looks like this. So this is how we convert an ordinary tree into a rooted tree at vertex B. Okay. Okay, a different rooted tree. You see, you can keep going. This time, instead of B, I'm calling C the root. Okay. Different rooted tree results. Okay. The one at the top is the root. Okay, that's the way we designate it. So once I put this up here, okay, so C's there. In the last one, it wasn't like that. But this is how we can transform this into C being the root of this particular graph. Review of rooted tree terminology. Yes, we already done this, parent, child, sibling. Here's a root. Okay, those are the siblings. Ancestors, well, ancestors of K. There, ancestors of K are these. Okay, there they are. The ancestors of D are these. No, the ancestors of D is A. Ancestor, oh God almighty, K. Okay, ancestor of D. These are the descendants of, oh, thank goodness. Descendants, I was reading ancestors. Ancestors of K goes back. Ancestors of K goes to F. Descendants of D are these nodes here. And we already called this leaves. Okay, these are the leaves right here, the ones that are terminus. Internal vertices are, they don't seem to be highlighted. Yes, it's internal vertices. These are leaves. Internal vertices are all of these, but not the root. I don't know why they're saying the root is an internal vertex. That's internal, that's internal, that's internal, that's internal. Is a root an internal vertex? I suppose you can say it is, but it's usually designated as separate, as a special root. But it is internal. It definitely is internal. Okay. Height versus depth. Okay, this is a very important distinction. The depth of a node is the number of edges from the node to the tree's root node. From the node to the root node, okay? The height of a node is the number of edges of the longest path from the node to the leaf. So it's the opposite. Depth and height obviously are the opposite, okay? A leaf node will have a height of 0, okay? The height of a node and number of edges on the longest path from the node to a leaf. A leaf node will have a height of 0, obviously. Okay, height of the node is the node. The height of a node is the number of edges on the longest path from the node to a leaf. And so a leaf will have height 0. Does that make sense? A root node will have the depth 0. You see, they're the opposite of each other. Oh, recursive definitions. Look at these. This is this thing has a branching factor of 2. And look at how exponential it is. You see, this shows you the exponential nature of a binary tree, a full binary tree. It starts here and it splits off here. Each node has a branching factor of 2. These are branching factors of 2. And eventually, just look how it explodes. This is what an exponential explosion looks like. So, yes, we can have recursively defined rooted trees. So it's very simple. The set of rooted trees where a root tree consists of a set of vertices containing a distinguished vertex called a root, and edges connecting these vertices can be recursively defined. Basis step, a single vertex R is a rooted tree. A single vertex R is a rooted tree, root R. Recursive steps suppose that T1, T2, and all the way to Tn are disjoint rooted trees with roots, R1, R2, all the way to Rn, respectively. Then the graph formed by starting with a root r, which is not in any of the rooted trees, T1, T2, Tn, which is not in any of these trees. And adding an edge from R to each of these, of the vertices, all of these, is also a rooted tree. So that's the idea. Basis step, then we add edges, then we add edges again. We just recursively keep adding edges, okay, in this fashion. Please understand this. Since we covered recursion, you can see how we can recursively define trees, okay? Recursively define, in this case, a rooted tree. It doesn't work for just any old tree. It's a rooted tree that it's designed for. Okay, so spanning trees, okay? We know what a subtree is. I mean, there it is. This is subtree B, subtree D, okay? We talked about it already. Forest is a circuitless graph. A tree is a connected forest. A subforest is a subgraph of a forest. A connected subgraph is a tree of a tree is a subtree. Generally speaking, a subforest, respectively subtree, of a graph is its subgraph, which is also a forest, respectively. So here in mathematical field of graph theory, a spanning tree T of an undirected graph G is a subgraph that is a tree, which includes all of the vertices. You can see there are different ways of connecting these vertices. Very different trees fit all of these vertices. All right. See this blue one? Okay, that includes every one of these vertices. And then this one here, that includes every one of these vertices. So a spanning tree T of an undirected graph G is a subgraph that is a tree which includes all of the vertices of G. So that's the big blue thing, okay? In general, a graph may have several spanning trees, but a graph that is not connected will not contain a spanning tree. A graph that is not connected, okay, so all trees are connected, okay? If all of the edges of G are also edges of a spanning tree T of G, then G is a tree and is identical to T. That is, a tree has a unique spanning tree and it is itself, just like the idea of subset. Here, let's just have a look at this. 4 trees which together form a forest, okay? A spanning tree of a connected graph is a subtree that includes all the vertices of the graph, as we just said. If T is a spanning tree of graph G, then G minus T, all right, T being the spanning tree, by definition is this co-spanning tree, T sub superstar. Okay, so here we've defined a connected graph which has a spanning tree, and a co-spanning tree, which is the complement of T, actually. So here's an example. Example A has this spanning tree. As you can see, it's a different graph, a different tree. So that's not a tree, but this is a graph, which is a tree. This is a spanning tree of this graph. And this is the co-spanning tree. That's this thing minus that. It gives you these these edges, okay, and that point there. So you can see here exactly what we mean by this equation right here, having defined a co-spanning tree on top of a spanning tree. This is really valuable in computing science. Okay, now this is how you make spanning trees. At least I've included it for you. I haven't taken it out. I've just omitted it, that you're not responsible for it. But those of you that are interested, this is how you construct spanning trees. There's either the cutting down method or the building up method. So don't worry about that. That's not going to be on the exam. And just what are the 3 spanning trees associated with this graph? Well, there they are. I mean, that's a good exercise. I think you should know that. It's pretty obvious. Here's a graph, and this is a tree, this is a tree, and that's a tree. And they're all spanning trees because they are different and they contain all of the nodes of the original graph. Okay, a graph is connected if and only if it has a spanning tree. Well, connected graph is biconditional, is logically equivalent to spanning tree. Connected graph, a graph is connected if and only if it has a spanning tree. That's another way of saying it. Statement, a graph G is connected if and only if it has a spanning tree. Proof, G connected implies spanning tree. Repeatedly remove edges that are not bridges. Resulting subgraph H is connected and acyclic. It's a spanning tree, but it has all of the nodes. Spanning tree implies G connected, going the other way, implying this way, implying that way. The spanning tree consists of all vertices, therefore G has paths between all vertices, so G is connected. Again, the spanning tree connects all vertices, therefore G has paths between all vertices. G is connected. So you can get to any node from any other node. This is connected. We've already talked about this. The arity. What is the arity of this tree? It is 2. Okay? There's 3 leaf nodes. It's a 2-ary or binary tree. And it's a full binary tree because each node has a branching factor of 2. Counting edges. This is very important. Okay? When trees are used in algorithms or to model data structures, it is important to be able to compute various properties possessed by a tree, possibly as a function of the number of vertices, number of edges, or number of siblings, for example. Let's just stick with edges and vertices. That's what we have down here. It's a very foundational equation right here. And it just fits right in with what we were saying before with products with additions between them, the n-1 factor. These parameters others associated with trees are interrelated. That is, each is often constrained and therefore determined by the values of the others, obviously. Okay, so in a connected tree, the number of edges E is related to the number of vertices N by the following theorem. E equals n-1. All right. The number of edges E equals the number of nodes minus 1. You can just see that now in a tree. All right, let's do it by induction. Base case n equals 1. Well, a single vertex tree has no edges. Inductive hypothesis. Assume any tree with k vertices has k-1 edges. That's what we're assuming here. Inductive step. Consider a tree with k plus 1 vertices. Now, k vertices to k plus 1. Every tree has at least one leaf, vertex of degree 1. Remove a leaf and its edge implies the remaining graph is still a tree with k vertices, obviously. By the inductive hypothesis, the remaining tree has k-1 edges. Adding back the removed leaf and edge, the total edges are k-1 plus 1 equals k. So by induction, a tree of n vertices has n-1 edges. Well, this is inconsistent. That says E, that says N. Okay, this has probably got to change down here. Yes, that's got to change. Well, no. It's still true. Okay. Yeah. Okay, that's consistent. That's good. I was just checking. Yes, this is fine. This is fine. This makes perfect sense. And you just start off in general terms, but this is the number of, you can't say n equals n-1, obviously. But then you state that n vertices has n-1 edges, again, like the number of products added together. There are n-1 subtractions or addition signs to the n products. Okay, it's the same exact thing. So this, you can't say n equals n-1. So it's just simply what we've done here. Counting vertices now. Here we counted edges. Now we're going to count vertices. Counting vertices is fundamental when combined with edges, degrees, height, and structure. In rooted trees, vertices are of 2 types, internal and leaves. Knowing the number of each type is important for analysis. Okay, this, of course, is for big, very, very big working data sets. For full Emery trees with n vertices, well, let I be the number of internal vertices, lambda the number of leaves. Then we have key formulas, internal vertices and total vertices. So we have, where's M? Where is M defined here? Oh, God. Okay, it's an Emery tree, so that's the maximum branching factor, times I, the number of internal vertices, equals the number of nodes, right? Oh, sorry, the number of, yes, nodes, vertices, minus 1, which applies. You solve for I, you get this formula here. That's for internal vertices. For leaves, well, lambda equals this formula if you just didn't turn this around for this. Edges, E equals M times I, okay? These formulas allow to compute vertices and edges in a full, say, binary tree, for example. Okay, that's useful. So counting edges, counting vertices, know how to do that, know what that's all about. It's that simple. So by inspection, we could look at those formulas. Okay, by inspection, there are 39 edges, 40 vertices, three children for every internal vertex, 13 internal vertices, 27 leaves. So when we plug it in, m times I equals 3 times 13 equals 39, which is n minus 1. 40 minus 1. So the whole thing's consistent, counting vertices, okay? And so you can see this is a full trinary tree, okay? It's a branching factor of 3. Every node has it except the leaves. Balanced trees, okay? Balanced trees are another kind of tree we must consider. It is the case where, for example, you're making a database, a file system, accessing files. That's really the important thing here. And you want a balanced tree so that, certain... Oh, sorry about that. Looks like lunch is on. Anyway, never mind. So, balanced tree, you want to make sure that that tree isn't imbalanced so that accessing files down here is longer than accessing files. You want everything to be sort of fair. Every file should be accessed in a fair way. Okay, so, and we make it so that a balanced tree, that's not balanced, this one is, if the maximum distance from one level to the next doesn't exceed 1, like here, okay? Okay, binary trees, sort of like decision trees, 0, 1, true, false, yes, no. Deciding between two alternatives is fundamental logical reasoning, so binary trees are a big deal. Key properties are height, number of leaves, and the relation. Say, the number of leaves is less than or equal to 2 to the h, okay? It goes down 1, 2, 4, 16, 32. But that's for a full binary tree, so that's why it's less than or equal. So if it's full, that's equal. A complete binary tree, recursive definition, if there's just one leaf, that's the base case. Recursive step is adding leaves according to the inductive hypothesis, okay? To grow a tree from height h minus 1 to h, each leaf adds 2 new leaves, okay? The number of leaves in a complete binary tree of height 1, 2, and 3 are lambda 1 equals 2 to the 1. Lambda 2 is 2 squared equals 4, like I said. Okay. Lambda 2 to the 8, that looks like E. Using formal inductive reasoning, we can hypothesize that lambda h is 2 to the h. Let's prove it for a full binary tree, complete binary tree. So this is definitely a full binary tree. To prove that lambda 0 is 2 to the 0, proof. Lambda 0 equals 1, which is 2 to the 0, inductive hypothesis. Let's see if we can prove this now. To prove that, prove lambda h plus 1 equals 2 times lambda h from the recursive definition, and 2 equals 2 times 2 to the h by substituting the inductive hypothesis. And so, what's this? Well, I don't know what that 3 is doing there. Hypothesis, that doesn't make sense. Anyway, you know what's going on here. We've proven we can use the inductive hypothesis to get to the next step on the rung, which is 2 to the h plus 1. So therefore, the number of leaves in a complete binary tree of height h is given by 2 to the h. We've proved that that's true. What the heck? My importance. This looks surprisingly the same. Binary trees. Okay, the result places a cap on the number of leaves that can occur in a binary tree with the cap determined by the height of the tree. In effect, for a binary tree, the height h, there can be at most 2 to the h leaves. This is so obvious. Now, the following example shows 3 full binary trees. However, the one on the left is not the one. Only the leftmost tree is complete. Okay, this is full. It's a full because the branching factor is 2 everywhere. This is full. This is full and balanced. This is full, balanced, and complete. All right. So we have another final theorem, I think, here. Every full binary tree has an odd number of vertices. Every full, that means branching factors are all the maximum, binary 2 tree has an odd number of vertices. And yeah, that makes perfect sense. Every vertex produces 2 vertices, right? Except the here, use the handshake lemma. Every graph has an even number of vertices of odd degree. Okay, so apart from the root, every vertex in a binary tree is of odd degree. We know that there are an even number of such odd vertices. Therefore, when the root, which is of even degree, is added to this number, the total number of vertices is odd. Once again, apart from the root, every vertex in a binary tree is of odd degree. Every vertex in a binary tree is of odd degree. You see, something's coming into it and 2 are coming out. So it's a degree 3. Okay, but the root is degree 2. So when the root is, okay, we know that what is this theorem again? Use handshake theorem. Every graph has an even number of vertices of odd degree. Okay. All right. So this proves it for a full binary tree. So when the root is added, which is even, the total number of vertices is odd. Okay. It's even plus odd is odd. Every graph has an even number of vertices of odd degree. Okay, the sum of all degrees is equal to twice the number of edges. The sum of all the degrees is equal to twice the number of edges. We had that in the first presentation. Since the sum of the degrees is even, and the sum of the degrees of vertices with even degree is even, the sum of degrees of vertices with odd degree must be even. That's clear logic. If the sum of the degrees of vertices with odd degree is even, then there must be an even number of those vertices. Every graph has an even number of vertices of odd degree. That's a lemma that follows from this. Well, this is the end. You can see applications of trees are in search and artificial intelligence, obviously, binary decision trees, search strategies. This is depth first search. So you go down here all the way, then you come back and investigate here, and here, and then you go back and investigate this, and then you start going down the other subforest or subtree. Whereas breadth first search, you go here, then you go to there, then you go to there, there, and then you go to there. So you're going breadth first search, and here you're going depth first, okay? And here you can see how the application of trees is good for biochemistry, application of trees in sorting. You'll see this in 220, Compute 220. Data structures, again, Compute 220. Games, we've seen that already. Data structures for data set. I don't know what that's doing here. I don't know why that's there. Okay, here, this is good. This is for the compiler syntax tree. This is how you would do this, execute this formula using a tree, okay, in a compiler. That's the syntax tree. You can see so that it's A gets added to B and multiplied by C. Okay. Tree data structures everywhere. They use it in biology, and that is all I want to talk about. So that's all. We've not finished the course yet. I'm going to show you 2 videos next week and I'm going to discuss the final. So next week will be, at least a 3-hour lecture to prepare you for the final exam, which is on the 22nd. If you have any questions, you know that you just have to contact me. There's no mystery there at all. Just have to contact me. And other than that, it's been a pleasure, and we'll see you next week. Cheerio.